The year is 1940, and across the English Channel, German bombers are reducing British cities to rubble at a rate that makes reconstruction seem impossible. In London alone, the Luftwaffe has destroyed over 30,000 buildings. The mathematics are brutal. Traditional construction requires skilled masons, bricklayers, and carpenters who are either fighting overseas or already working around the clock. A single brick building takes 6 months to construct under normal conditions. Britain doesn't have 6 months. It doesn't have the labor. It doesn't have the materials. And most critically, it doesn't have time to train replacements for the craftsmen who built Victorian England. In a cramped office in the Ministry of Works, civil engineer Oscar Faber stares at damage reports that read like architectural obituaries. Entire neighborhoods gone. Hospitals, schools, factories, homes, all reduced to brick dust and twisted steel. The immediate problem isn't just shelter for bombed-out civilians, though that's catastrophic enough. The real crisis is industrial capacity. Britain's war production depends on factories, and you can't build Spitfires in buildings that don't exist. Conventional concrete requires steel reinforcement bars, rebar, twisted into cages that give the concrete tensile strength. But steel is the single most precious commodity in wartime Britain. Every ton of steel that goes into building construction is a ton that can't become tank armor or ship hulls. The Admiralty is already screaming that there's not enough steel for destroyers. The idea of using it for warehouse floors is almost treasonous. Faber's team has been tasked with the impossible: design a construction method that uses no steel, requires no skilled labor, builds faster than bombing destroys, and costs less than traditional masonry. Oh, and it needs to be stronger than brick because the next air raid is coming whether the building is finished or not. The answer, when it arrives, comes from an unexpected direction: a forgotten French gardener and a Roman engineering technique that's been obsolete for 1500 years. Joseph Monnier died in 1906, largely unknown outside horticultural circles. He'd been a gardener at the Palace of Versailles who got frustrated with clay pots breaking when he moved his orange trees. In 1867, Monnier patented a solution: concrete reinforced with an iron mesh. He used it to make planters, then water tanks, then eventually bridges. His invention, ferroconcrete, became the foundation of modern construction. But Monnier's real innovation wasn't adding metal to concrete. It was understanding that concrete's fundamental weakness, its inability to handle tension, could be compensated by embedding something else inside it that could. The concrete handles compression forces beautifully. The embedded material handles tension. Together they create a composite stronger than either component alone. By 1940, this principle is so standard that engineers can't imagine building any other way. Every concrete structure in Britain contains steel reinforcement. It's simply how concrete works. Except there's no steel available, which means, according to conventional wisdom, there's no way to build with concrete. Oscar Faber doesn't accept conventional wisdom. He's spent the past 3 weeks reading every historical text on ancient construction he can find. The Romans built the Pantheon with a concrete dome spanning 143 feet, and it's still standing after 2,000 years. They did it without any steel reinforcement because steel didn't exist in any useful quantity. How did they accomplish that? The Roman secret was shape. The Pantheon's dome isn't just a hemisphere. It's a compression structure where every part of the curve is pushing against every other part, creating what engineers call a compression ring. The forces flow through the material in pure compression, never in tension, which means the concrete never needs to resist pulling forces. It only needs to resist being squeezed, which it does spectacularly well. But Britain in 1940 doesn't need domes. It needs rectangular buildings, factories, warehouses, structures with vertical walls and flat roofs. You can't just curve everything, or can you? Faber's breakthrough moment comes when he's examining bomb damage at a collapsed warehouse. The building had a traditional flat concrete roof supported by steel beams. The blast had knocked out the beams, and the concrete, unable to support itself in tension, had simply fallen straight down in massive slabs. But nearby, a Victorian railway tunnel with a curved brick ceiling had survived the same bombing untouched. The arch had distributed the blast forces around its curve and into the ground. What if you could build an entire structure using compression-only geometry? What if you could eliminate steel not by finding a substitute, but by designing buildings that never put concrete in tension in the first place? The theoretical answer is elegant. The practical application is going to be extraordinarily difficult. Faber assembles a team of structural engineers, concrete specialists, and one particularly eccentric mathematician named Alan Arnold Griffith, who normally works on turbine blade design but has a side obsession with structural optimization. Griffith has been developing theories about how materials fail under stress, and his insights prove crucial for understanding how to design concrete structures that work in pure compression. The team starts with first principles. A flat roof is structurally inefficient because it's essentially a horizontal beam spanning space. Beams bend, and bending creates tension on one surface and compression on the other. That's why you need reinforcement. But an arch doesn't bend, it compresses. Every part of an arch is being squeezed, never pulled. If you could make a building entirely from arch shapes, you could theoretically eliminate all tension, which means eliminating all need for steel reinforcement. The Roman Pantheon proves it's possible. But that's a dome, a three-dimensional arch that curves in all directions. What about practical industrial buildings that need large floor spaces and vertical walls? You can't put a dome on a factory. The solution emerges from studying barrel vaults, the curved ceilings common in medieval architecture. A barrel vault is essentially an arch extended in one direction, creating a tunnel shape. Medieval churches used them extensively, built from stone blocks that could only handle compression. If medieval masons could create large spaces with barrel vaults, why couldn't modern engineers do the same with concrete? The mathematics are complex, but the geometry is simple. Design the building as a series of parallel barrel vaults. Each vault acts as a continuous arch, distributing all loads through compression. The end walls can be vertical, but the roof and side walls follow the curve. The thicker you make the concrete shell, the heavier loads it can carry. The wider the span, the lower and flatter the curve needs to be to maintain structural stability. Griffith runs calculations for weeks, filling notebooks with equations that predict how concrete shells of various thicknesses and curvatures will behave under different loads. The numbers reveal something remarkable. A concrete shell just 4 inches thick, if properly curved, can span 60 feet and support the weight of several feet of earth on top. No steel required. The catch is that the curve must be mathematically precise. Get the geometry wrong by even a few degrees, and the structure will try to flatten under load, which introduces tension, which causes failure. By March 1941, they have a theoretical design. Now comes the hard part, actually building one. The first prototype goes up at a military testing ground in Kent. The design is deliberately modest. A barrel vault 20 feet wide, 40 feet long, and 12 feet high at the crown. The concrete is poured over a temporary wooden form, curved timber ribs that support the wet concrete until it cures and gains strength. This formwork is expensive and labor-intensive to build, which seems to violate the whole premise of quick, cheap construction. But Faber's team has a plan. Build one set of forms, use them to cast one vault, then disassemble the forms and reuse them for the next vault. A single set of formwork can theoretically build dozens of structures. The concrete mix is critical. Standard concrete is too weak for thin shell construction. The team develops a higher strength formula using smaller aggregate stones and more cement, creating a denser, stronger material. They add waterproofing compounds because these roofs can't leak, and water infiltration would be catastrophic. The mix costs more per cubic yard than standard concrete. But since the shells are so thin, each building uses far less total concrete than conventional construction. Pouring the vault is an exercise in precision. The concrete must be applied evenly across the curve to prevent uneven loading during curing. Too thick in one spot and that section will sag. Too thin and it won't achieve structural strength. The crew works in sections, applying concrete and smoothing it to exact thickness before moving to the next section. The entire pour must be completed in a continuous operation because joints or seams introduce weak points. 4 weeks later, the wooden forms come down. The structure stands on its own for the first time, a graceful arc of concrete that looks impossibly thin to support its own weight, let alone any additional load. The testing begins immediately. Engineers pile sandbags on the roof, calculating the weight to simulate various load conditions. The shell flexes slightly, barely perceptibly, then holds. They add more weight. The vault holds. They simulate blast effects by detonating small explosive charges at various distances. The curved surface deflects the shock waves. The structure holds, but the real test comes from an unexpected source. A spring storm hits Kent with heavy rain and strong winds. The prototype vault is still technically under test, not approved for occupancy, so it sits empty during the weather. The next morning, Engineers arrive to find the structure completely intact. No leaks, no cracks, no damage. Inside, the concrete is dry and the temperature noticeably warmer than outside. The thermal mass of the concrete, even just 4 inches of it, has absorbed and retained heat. The curved shape has shed water perfectly, and most impressively, the wind loading, which was one of their biggest theoretical concerns, has had zero effect. Oscar Faber writes his report to the Ministry of Works with cautious optimism. The design works. It can be built without steel reinforcement. It's demonstrably strong enough for industrial use. And most critically, once you have the formwork built, construction time for each subsequent vault is approximately 3 weeks from groundwork to finished building. The ministry's response is bureaucratically predictable. Prove it works at scale before we commit resources. Build a full-size industrial structure and show us it can handle real operational loads. By summer 1941, a full-scale prototype is under construction at a munitions factory in the Midlands. This vault is ambitious, 40 feet wide, 80 feet long, with vertical sidewalls that transition into the curved roof. The floor space is large enough to house production, machinery, storage, and worker stations. The design includes several innovations learned from the Kent prototype. The concrete thickness varies, thicker at the base where compressive forces are highest, thinner at the crown where loads are lighter. The end walls are poured separately with windows and door openings already formed, and the wooden formwork is designed to be assembled and disassembled in sections, allowing reuse with minimal carpentry skill. The construction crew is deliberately selected to prove a point. No skilled masons, no experienced concrete workers, just general laborers with basic carpentry skills and the ability to follow instructions. If this construction method requires expertise, it's useless for wartime deployment when expertise doesn't exist. The crew struggles initially. Pouring concrete overhead while maintaining even thickness proves physically demanding and technically difficult. The temporary formwork sags in several places, requiring emergency shoring. One section of the curve is slightly off specification, creating a flat spot that engineers worry might concentrate stress, but the crew learns fast. By the time they're working on the roof section, the operation has become almost routine. Mix concrete, transport it to the form, pour, smooth, move to the next section. 5 weeks after breaking ground, the formwork comes down. The vault stands complete. It's not beautiful by conventional architectural standards. The exposed concrete is industrial gray. The curve is utilitarian rather than elegant, and the overall aesthetic is somewhere between a railway tunnel and an aircraft hangar. But it's standing. It costs a fraction of conventional construction, it used zero steel, and it's ready for immediate use. The munitions factory moves in equipment the following week. Heavy presses, assembly tables, storage racks, everything a functioning production facility needs. The vault handles the loads without complaint. The workers report that the interior stays remarkably comfortable, cool in summer, warm in winter, with excellent acoustics that reduce the industrial noise to manageable levels. The curved ceiling creates natural air circulation that ventilates the space without mechanical systems. 3 months later, a German bombing raid hits the factory complex. High explosive bombs crater the grounds, destroy several traditional brick buildings, and leave the entire facility looking like a lunar landscape. Faber's concrete vault takes a near miss, close enough that shrapnel pockmarks the exterior surface and the blast wave strips away some of the window frames. But the structure itself, intact. The production equipment inside is undamaged. The factory resumes operations within 2 days. That single test, more than any engineering report or mathematical proof, convinces the Ministry of Works. By December 1941, they're authorizing mass production of these concrete vaults across Britain. The deployment scale is staggering. The ministry identifies over 300 sites requiring immediate construction: factories, warehouses, storage depots, repair facilities. Each needs to be built in weeks rather than months, using materials that don't compete with military needs. The concrete vault system, now officially designated as Type A structural units, becomes the solution. The formwork manufacturing becomes its own industrial operation. Specialized factories produce the curved timber sections, precisely cut to mathematical specifications. Each set of forms, when assembled, creates a perfect parabolic curve that will produce a structurally sound vault. The forms ship flat on rail cars, assemble on site in 2 days, get used to cast a vault, then disassemble for transport to the next location. A single set of forms can build 20 or 30 structures before the wood wears out. The concrete sourcing requires creative logistics. Britain has plenty of cement production capacity and abundant aggregate stone in quarries across the country. The limiting factor is transportation. Moving millions of tons of stone and cement to hundreds of construction sites requires a level of railway coordination that rivals military supply chains. The ministry establishes concrete production priorities that rank different construction projects. Munitions factories get priority 1. Aircraft repair facilities get priority 2. General warehousing gets priority 3. Civilian housing, desperately needed, falls to priority 7. By mid-1942, vaults are going up at a rate of 15 per week across Britain. The construction crews have evolved their techniques through hard experience. They've learned that building in cold weather requires heating the concrete during curing to prevent freeze damage. They've discovered that surface finish matters less than structural integrity, so they skip the labor-intensive smoothing operations and accept rough concrete surfaces. They've developed rapid formwork systems that reduce assembly time from 2 days to 8 hours. The design variations expand as engineers gain confidence in the system. Some vaults are built partially underground, using earth berms against the sides for additional blast protection and thermal insulation. Others are built in clusters, sharing common walls to maximize floor space efficiency. Several experimental designs incorporate multiple parallel vaults with connecting passages, creating vast covered areas for aircraft assembly or tank maintenance. The most ambitious project emerges in late 1942 when the ministry approves construction of an entire underground factory complex in the Cotswolds. The design calls for 20 parallel vaults, each 100 feet long and 40 feet wide, buried under 15 feet of earth. The idea is to create bomb-proof production space for critical aircraft components. The construction takes 9 months and requires moving thousands of tons of earth, but when finished, the facility houses over 300 workers in a space that's essentially invulnerable to aerial attack. The thermal properties of these structures create unexpected benefits. The concrete's thermal mass naturally moderates temperature swings. In summer, the interior stays 20 degrees cooler than outside. In winter, the residual heat from machinery and workers gets retained by the concrete, reducing or eliminating heating requirements. Several facilities report that they're using no supplemental heating despite Britain's damp, cold winters. The concrete simply absorbs heat during occupied hours and radiates it back slowly overnight. The acoustic properties prove equally valuable. The curved surface diffuses sound waves instead of reflecting them directly, reducing echo and reverberation. Factory workers report being able to hold conversations at normal volume despite operating heavy machinery. The noise reduction isn't just about comfort. It's about safety. Workers can hear warning signals, communicate problems, and maintain situational awareness in ways that traditional rectangular buildings with hard parallel walls don't allow. But these vaults aren't perfect, and field experience reveals several significant drawbacks. The curved shape makes interior space utilization inefficient. Vertical walls allow floor-to-ceiling storage, but curved walls create dead space where the wall meets the floor. Several facilities solve this by building interior platforms or storage lofts, but that adds cost and labor. The lack of windows in the curved sections makes the interiors dark and requires artificial lighting even during daylight hours. Early facilities use gas lamps, but the open flame in enclosed concrete spaces creates carbon monoxide hazards. The switch to electric lighting helps, but electrical infrastructure in wartime Britain is already overtaxed. The waterproofing proves less reliable than hoped. The concrete itself is waterproof, but the joints where end walls meet the curved vault sections create potential leak paths. Heavy rains reveal dozens of facilities with seepage problems. The solution involves applying tar-based sealants and installing interior drainage systems, but this requires ongoing maintenance that the original design was supposed to eliminate. Perhaps the biggest challenge is psychological. These structures look and feel industrial, almost oppressive. Workers complain about feeling like they're laboring in tunnels or caves. The lack of natural light affects morale. The constant curve of the walls creates spatial disorientation for some people. Several facilities experiment with painting the interiors white or adding decorative elements, but there's only so much you can do to make a concrete tunnel feel welcoming. Despite these limitations, the vaults serve their purpose spectacularly well. By war's end, over 800 have been constructed across Britain. They house munitions, production, aircraft repair, vehicle maintenance, supply storage, and administrative offices. More importantly, they've kept British industrial capacity functioning despite years of aerial bombardment. The Luftwaffe has destroyed thousands of conventional buildings, but the concrete vaults survive raid after raid, keeping production lines running when the war's outcome hangs in the balance. The true measure of their success comes in 1944 when Germany begins launching V-1 flying bombs at London. These unmanned cruise missiles carry 1-ton warheads that produce devastating blast effects. Traditional buildings within 200 feet of a V-1 impact are typically destroyed, but concrete vaults prove remarkably resistant. The curved shape deflects blast waves around the structure rather than absorbing them directly. Several vaults take direct hits that would have leveled conventional buildings, yet remain standing with repairable damage. Workers sheltering inside during raids survive impacts that would have killed them in traditional structures. After the war ends, Britain faces the same question that plagued America with its Quonset huts: what to do with hundreds of specialized wartime structures that nobody particularly likes, but everyone admits are useful. The initial plan calls for demolishing the vaults as soon as conventional construction can replace them. But conventional construction in 1945 Britain is even more constrained than during the war. The country is broke, the labor force is transitioning from military to civilian work, and the housing shortage has reached crisis levels. The concrete vaults, ugly and utilitarian as they might be, represent functional space that costs almost nothing to maintain. The government establishes a surplus property program that offers vaults to private buyers at bargain prices. A complete vault, including the land it sits on, can be purchased for £500. Buyers are responsible for any modifications needed to adapt the structure for civilian use. Within a year, over 200 vaults have been sold to farmers, small manufacturers, and entrepreneurs looking for cheap commercial space. The agricultural community embraces the vaults enthusiastically. Farmers discover they make excellent grain storage facilities. The concrete is rodent-proof, the curved roof sheds rain perfectly, and the thermal mass keeps interior temperatures stable, preventing moisture accumulation that causes grain spoilage. Several dairy farmers convert vaults into milking parlors, finding that the cool, stable environment is ideal for dairy operations. The fact that these structures are frankly ugly doesn't matter when they're sitting in a field, and functional utility is the only design criterion that matters. Manufacturing operations face different challenges. The curved walls make installing conventional machinery and assembly lines difficult, but small-scale manufacturers, machine shops, and repair facilities work around these limitations. They build wooden interior structures to create vertical surfaces for mounting equipment. They install overhead crane systems that use the curved ceiling as an advantage, creating lifting capacity that would require expensive structural support in rectangular buildings. A surprising number of post-war British manufacturing firms spend their formative years operating from converted concrete vaults, growing their businesses in structures that cost almost nothing to acquire and maintain. The creative adaptations get genuinely innovative. One vault in Yorkshire becomes a theatre company's rehearsal and performance space. The acoustics that made factory noise tolerable turn out to be excellent for theatrical sound. The lack of windows creates perfect darkness for lighting effects. The company adds a wooden stage, audience seating, and basic amenities, creating a functional performance venue for less than the cost of renting conventional space for a year. A vault in Cornwall becomes an art studio collective, housing 6 painters and sculptors who appreciate the north-facing light from windows cut into the end walls and the vast, uninterrupted ceiling that allows large-scale work. The concrete walls turn out to be perfect for hanging heavy sculptures or mounting large canvases. The industrial aesthetic becomes part of the artistic identity. Perhaps most surprisingly, several vaults become homes. Not comfortable homes by conventional standards, but homes, nonetheless, for families desperate for any housing during the post-war shortage. These conversions require significant work: interior walls, insulation, proper windows, heating systems, but the basic structure is sound and weatherproof, which puts it ahead of many alternatives. A few families become so attached to their vault homes that they continue living in them decades later, long after they could afford conventional housing. The education sector finds unexpected uses. Several rural schools adopt vaults as gymnasiums or assembly halls. The clear span interior makes them perfect for physical education, and the acoustic properties work well for large gatherings. Students grow up playing basketball and attending assemblies in structures that once housed aircraft engine repair operations, never knowing or caring about the military origins. The religious community discovers similar utility. Small congregations, particularly newer evangelical and Pentecostal churches, find that vaults offer affordable worship space. The acoustics enhance singing and speaking. The curved ceiling creates an interesting aesthetic that some congregations interpret as spiritually significant, a modern interpretation of the vaulted spaces in medieval cathedrals. At least 24 British churches still hold services in converted concrete vaults. The industrial origins, long since obscured by paint, lighting, and decades of spiritual use. By the 1960s, most surviving vaults have found permanent purposes. They're no longer temporary wartime expedients, but established parts of Britain's built environment. A few have been demolished when their land becomes valuable for redevelopment, but the majority persist because they're simply too useful and too indestructible to justify removal. The concrete that was supposed to last 10 years has already lasted 25 with minimal maintenance. Engineers inspecting them find the structures as sound as the day they were built. The concrete hasn't degraded. The compression-only design means there's no steel reinforcement to corrode. These buildings, intended as emergency wartime measures, have accidentally become near-permanent architecture. The international influence emerges gradually. French engineers studying British wartime construction techniques adapt the concrete vault concept for post-war reconstruction. They refine the design, using thinner shells and more sophisticated curved geometry, creating what becomes known as voussoir arch construction. The technique spreads to French colonies, where it proves ideal for tropical climates. The concrete resists humidity better than wood. The curved shape sheds monsoon rains, and the thermal mass keeps interiors comfortable without mechanical cooling. Spanish architect Felix Candela takes the concept even further in the 1950s, designing thin-shell concrete structures with complex hyperbolic paraboloid curves. His buildings pushed the mathematical limits of compression-only design, creating soaring architectural spaces from concrete shells as thin as 2 inches. Candela acknowledges the British wartime vaults as inspiration, though his work transforms the utilitarian military structures into sculptural landmarks that redefine architectural possibilities. The technique reaches its apotheosis in developing nations during the 1960s and 1970s. Engineers working in Africa, Asia, and Latin America faced the same constraints that confronted Britain in 1940. Limited skilled labor, scarce steel, urgent need for durable structures. The concrete vault solution, now refined by decades of experience, proves ideal. Construction programs build schools, clinics, and community centers using locally produced concrete and unskilled labor. The curved roofs naturally shed tropical rains, the thick concrete walls provide thermal mass that moderates temperature swings, and the compression-only design eliminates the steel reinforcement that tropical humidity would corrode anyway. By the 1980s, an estimated 10,000 structures worldwide owe their design heritage to Oscar Faber's wartime innovation. Most people using these buildings have no idea they're occupying spaces designed under the pressure of German bombing raids. The concrete vaults have become so integrated into vernacular architecture that their military origins are forgotten. The modern rediscovery begins in the 1990s when sustainable architecture movements start examining historical building techniques. Researchers studying low-embodied energy construction methods identify the British wartime vaults as early examples of several principles that contemporary green building advocates promote: using local materials, minimizing steel consumption, designing for passive thermal control, creating durable structures that don't require ongoing maintenance or energy inputs. Several architectural historians successfully campaigned to preserve notable vault structures as heritage sites. The underground factory complex in the Cotswolds becomes a museum documenting wartime industrial history. A cluster of vaults in Kent that served as an aircraft repair facility is restored and repurposed as a creative industries center, housing designers and tech startups in spaces that once housed hurricane fighter repairs. The industrial aesthetic that was considered ugly in 1945 is reappraised as brutalist or industrial chic by a generation that values authenticity and historic character. Contemporary engineers rediscover the structural efficiency. Computer modeling confirms what the 1940s engineers calculated by hand. Properly designed compression structures use materials with extraordinary efficiency. A concrete shell building uses approximately 1/3 the material of an equivalent conventionally reinforced structure while achieving equal or superior strength. This efficiency matters enormously when calculating carbon footprints and environmental impacts. Less concrete means less cement production, which means less CO2 emissions. Several modern architecture firms have begun designing contemporary concrete shells, using 3D modeling software to create complex curves that would have been impossible to calculate in the 1940s, but follow the same compression-only principles. These buildings look nothing like the utilitarian wartime vaults, but the engineering DNA is identical. The mathematical curves, the thin shells, the elimination of tension forces, all trace back to Oscar Faber's team working in a London office while bombs fell overhead. The most direct contemporary descendant appears in disaster relief architecture. Organizations providing emergency shelter after earthquakes, hurricanes, or conflicts face the same constraints that drove the original vault development: minimal materials, unskilled labor, rapid deployment, structural durability. Several modern emergency shelter systems use thin concrete shells poured over inflatable formwork that can be deflated and reused, allowing construction of permanent structures in days rather than months. The curved profiles resist wind and earthquake forces better than conventional rectangular buildings, and the concrete provides far better durability than temporary materials. Hurricane-resistant housing programs in the Caribbean have embraced concrete shell construction after decades of watching conventional buildings destroyed by storms. A properly designed concrete vault can resist Category 5 hurricane winds that would level traditional frame construction. The curved surface naturally deflects wind rather than presenting flat surfaces that catch full wind loads. Several islands now require new construction to meet standards that essentially mandate vault-like geometry for any structure expected to survive hurricane season. The space architecture community has encountered the same principles from a different direction. Engineers designing habitats for lunar or Martian bases need structures that can be built with minimal equipment, resist extreme temperature variations, and provide protection from radiation and micrometeorites. Several proposed designs feature concrete-like materials formed into curved shells that work in pure compression, eliminating the need for steel reinforcement that would be nearly impossible to manufacture in space. The optimal geometry, according to computer models, looks remarkably similar to the vaults Oscar Faber designed 85 years ago. The full circle moment comes in the 2010s when the British military, facing budget constraints and rapid deployment requirements, commissions a study on field construction methods. The study examines various historical military building systems, including the famous Nissen and Quonset huts, evaluating them against contemporary needs. The researchers encounter documentation about the World War II concrete vaults, a system so obscure that most military historians had forgotten it existed. The evaluation concludes that modern materials and construction techniques could produce updated versions of the vault concept that would outperform current military field structures. Fiber-reinforced concrete could reduce shell thickness while increasing strength. Modular formwork systems using modern materials could reduce construction time. Computer-controlled concrete placement could ensure uniform thickness and optimal curing. The fundamental design from 1941 remained sound, only the execution would improve. As of 2025, several hundred original British concrete vaults remain in use across the UK. Some are recognized heritage structures. Most are simply functional buildings that continue serving agricultural, industrial, or commercial purposes 8 decades after their construction. The concrete shows minimal degradation. The compression-only design means there's no hidden corrosion weakening the structure. These buildings, designed to solve an emergency wartime crisis, have accidentally achieved something rare in architecture: genuine permanence. The engineers who designed them are long dead. Oscar Faber passed away in 1956. His concrete vaults a minor footnote in an otherwise distinguished career. Alan Griffith became famous for different work entirely, his contributions to turbine design overshadowing his structural mechanics insights. The construction workers who built these vaults, the factory workers who occupied them, the families who converted them to homes, none left detailed records. This is history written in concrete rather than words, in structures that persist long after their creators and original purposes have faded. Stand inside one of these vaults today and you're experiencing a direct connection to 1941. The curve of the ceiling is the same curve that British engineers calculated by hand while bombs fell on London. The concrete you see is the same concrete poured by laborers working through air raid warnings. The structure around you represents a moment when necessity forced innovation, when the absence of steel forced engineers to remember ancient principles, when the urgency of war drove creativity that peacetime probably never would have produced. The vault's persistence testifies to something fundamental about good engineering: solutions that work with rather than against natural forces, that embrace constraints rather than fighting them, that achieve strength through geometry rather than brute material excess. These solutions have timeless value. The specific context changes. The available materials evolve. The construction techniques improve, but the underlying principles remain constant because they're rooted in physics that doesn't change. Oscar Faber and his team probably never imagined their emergency wartime shelters would still be standing 85 years later, still serving useful purposes, still demonstrating that sometimes the best solutions emerge not from unlimited resources, but from creative responses to severe constraints. They solved an impossible problem with concrete mathematics, and the willingness to abandon conventional assumptions about how buildings must be built. The concrete vaults they created proved that steel reinforcement, though tremendously useful, isn't absolutely necessary. That ancient compression-only principles, properly applied with modern materials, can create structures as strong as any conventionally reinforced building. That the same geometric principles that let Romans build the Pantheon could help Britain survive the Blitz. That sometimes the most valuable innovations come not from imagining the future but from remembering the past, understanding why old solutions worked, and applying those lessons to new problems. In the end, these obscure concrete tunnels scattered across the British countryside represent something larger than their modest architectural presence suggests. They're physical evidence that crisis drives creativity, that constraints force innovation, that the best engineering often emerges when conventional solutions become impossible and people have to think differently. They're monuments to the idea that sometimes you don't need better materials or more resources, you need better thinking about how to use what you have. The vaults stand today as they stood in 1941, curved against the sky, unbeautiful but unbreakable, aging gracefully into architectural history while still serving whatever purpose current occupants require. They've housed war workers and peacetime farmers, airplane repairs and artistic creation, worship services and theatrical performances, all within the same unchanging concrete curves. They've survived bombing raids and winter storms, economic transformations and cultural shifts, remaining constant while everything around them changed. Perhaps that's the ultimate validation of their design. Good engineering transcends its original purpose. The best solutions work not just for the immediate problem but for challenges their creators never anticipated. Oscar Faber designed emergency wartime shelters. What he actually created were buildings that could serve any purpose, survive any condition, outlast any expectation, all without requiring the one material Britain couldn't spare: steel. The concrete vaults changed British industrial architecture, influenced global development practices, and demonstrated principles that remain relevant in contemporary sustainable design. But their real achievement is simpler and more profound. They kept people alive, kept factories running, kept Britain fighting when conventional construction methods would have failed. They solved an impossible problem with elegant simplicity, and they're still standing to prove it worked.